In today's video, we'll learn about fuzzy string matching. We'll start with a conceptual overview and then look at some examples in R, using several different algorithms. If you like this video, please be sure to subscribe to my channel so that I can continue making content like this. Before we talk about fuzzy string matching, let's talk about string matching more generally. Say we have two different data sets, and each one has a variable that contains the name of a company. In dataset number 1, this variable is called company_name, and in dataset 2, this variable is called name_of_company. If we want to combine the information from dataset 1 and dataset 2, we can simply do a join on the two datasets using the variable that they have in common. In the example we just looked at, the information contained in the two string variables, remember, those were called company_name and name_of_company, was the exact same across the two datasets. This made the merging of the datasets very straightforward. But what if the information had not been identical between the two sources of information? Enter fuzzy string matching. Often, we want to compare two strings that are referring to the same information, but the two strings are written slightly differently. This may occur because of typos, different spellings, slight differences in capitalizations, or different usage of non-alphanumeric characters. In cases like these, we can use something called fuzzy string matching. This is sometimes also referred to as approximate string matching. With fuzzy string matching, we can determine the similarity between two strings. If two strings have a high similarity score, we can say that they're a match. The higher the similarity score, the more likely the match is correct. Just like we can use, for example, the Euclidean distance to determine how similar two numeric vectors are, we can use some sort of distance metric to determine how similar two strings are. There are many different types of distance metrics for determining the similarity between two strings. For example, there's something called the Levenshtein Distance, which focuses on the minimum number of single character differences, that is, additions, substitutions, or deletions, between two strings. This is a fairly simplistic metric, and it works well for the examples we've seen so far. But what if our strings are a little bit more complicated? Well, we could try using a different distance metric, such as Gestalt Pattern Matching, also known as Ratcliff Obershelp Pattern recognition. This metric produces matches that look more correct to the human eye, since this metric focuses on finding the longest common substring between the two strings. We just talked about two different ways to compute the similarity between two strings, but there are many more. The metric that you choose is going to depend on your specific needs. For example, you may want to take into consideration things like the computational complexity of different algorithms, or consider which algorithms are readily available in a programming language of your choice. This leads us to part 2 of the video, where we'll talk about how to perform fuzzy string matching in R. We'll use a few different algorithms. For today's example, we'll be using one of the classic datasets that is used for approximate string matching. I got this dataset from Kaggle. I'll put the link in the description below, but you can also find it on my GitHub, along with the code and the slides from this video. I'm going to start by loading some packages. First, I'm going to load the tidyverse, and next I'm going to load the reticulate package. We will be using some Python packages, but I'll get to that a little bit later. Next, I'm going to set my working directory, and I'm going to be setting my working directory to the location where I've downloaded the dataset from Kaggle. Once I've got my working directory set, I'm going to load in the CSV file. I'm going to call it rooms. Let's take a look at the structure of this dataset. We've got 103 entries, 2 columns in total. The first column is called Expedia, and the second column is called booking.com. In this dataset, we can see that there are room descriptions on different websites that refer to the same room, though they're worded slightly differently. So for example, for the first row, we can see that at Expedia, there's a room that's called Deluxe Room with 1 king bed, and the same room on booking.com is listed as Deluxe King Room. And if we look at all of these observations in this data set, we can tell that the observation on the left in the Expedia column is very clearly supposed to be the same thing as the observation on the right column under booking.com. So it's clear to us that, for example, suite 1 king bed parlor is actually representing the same information as king parlor suite. Now in this data set, they've already been matched up perfectly with one another, but let's consider a situation where we did not know which observations matched with which. So for example, if I were to shuffle up the columns in this data set and then try to match them up with the correct strings, how would I go about doing that? First, I'm going to define two vectors that contains the strings that we want to match. I'm going to call them from_vec and to_vec. The reason why I'm calling it from and to is because a lot of the string matching algorithms that we're going to use take arguments like from and to. In the data set that we're working with, we have exactly 103 observations from Expedia and exactly 103 observations from booking.com, but you can imagine a situation where we had a different number of observations in each of the two data sources. So when we're defining a from vector and a to vector, what we're really saying is for each element in the from vector, we want to find the best possible match in the to vector. Totally arbitrarily, I'm going to choose the Expedia column as my from vector and the booking.com as my to vector. So if I take a peek at the head of the from vector, what we're going to be trying to do is for each observation in from_vec, so for example here for deluxe room 1 king bed, I'm going to look through all the observations in the to vector and determine which one of them is the best match for the string deluxe room 1 king bed. And then I'm going to iterate through each of the elements in the from vector, and my results are going to be the length of my from vector. So in this case, the length of my from vector and the to vector is the same, but that will not always be the case. So really we're starting with the from vector as our starting point, and our results are going to be the same size as our from vector. Now I mentioned a bit earlier that we're going to be using some Python packages. And the reason why is because most of the modern algorithms are not yet available in R, or if they are, the implementation is just not as good as it is in Python right now. So if we use the reticulate package, which is an R package, we're going to be able to work with Python packages really well from within RStudio without us really having to know anything about Python. There's going to be 3 Python packages that we're going to work with today. Those are called difflib, fuzzywuzzy, and polyfuzz. We're going to load in each of those Python packages using the import function from the reticulate package. First, I'm going to load difflib, and when I load it in, I'm going to assign this to an object in R that's called difflib in all caps. The Python package is actually written in lowercase letters. In order to do this, you will need to have Python installed. The difflib package comes installed with Python, so you won't need to install any additional Python packages in order to run this line of code. The next package that I'm going to load is called polyfuzz. And again, I'm using the import function from the reticulate package. The polyfuzz Python package does not come installed with Python, so you will need to install that beforehand. For this video, I'm assuming you already know how to install a Python package on your computer, and if not, there should be some great resources on YouTube. This package is quite large and it can take a couple of minutes to load into R. A moment ago, I mentioned that we're also going to be using a Python package called fuzzywuzzy, but I'm not actually going to load that in here using the reticulate package. There is an implementation of fuzzywuzzy in R, and the package is called fuzzywuzzy R. So I'm going to load that package, which is an R package. Now, ultimately, the fuzzywuzzy R package is behind the scenes using the fuzzywuzzy Python implementation, but the author of that package has gone ahead and created an R package for us so that the interaction is a little bit easier for us. There are some issues with the fuzzywuzzy R package, which I will get to in a few minutes, just as a heads up. Let's first look at the difflib package. So the difflib Python package has a function that's called get_close_matches. And if I want to use that function, I'm going to first start by writing out the name of the object in R that I've assigned the difflib package to. So I write difflib in all caps, followed by a $, and then I can write get_close_matches. And now I can use this function the same way that I would use it if I were instead using Python directly. The first argument that this function takes is the string that you're looking to find the best match for. So let's use the first element of our from vector. And remember, that is deluxe room, 1 king bed. And we want to find the best possible match that's found within our to vector. The next argument that we need to specify is how many matches we'd like to find. So if I type 1L, that's going to find the best possible match. But if I typed, for example, 3L, that would give me the top 3 matches that are in the to vector. And the last argument that we're going to talk about is cutoff. For right now, I'm going to set the cutoff equal to 0. And if I run this line of code, we can see in the console that the 3 best matches for deluxe room, 1 king bed from our from vector, the 3 best matches in our to vector are deluxe room dash 1 king bed, deluxe room dash 2 queen beds, and ocean view room with king bed. So those are all pretty close. If we take a look at our original data set, we actually see a different match than the one that was provided in the data set. But deluxe room, 1 king bed is indeed a very similar string to the one that we started with. So just to show you what would happen if I changed the third argument to say 1, it would only return the first top match. So the third argument controls how many matches are returned. And the fourth argument is going to control the cutoff value for the similarity score. We haven't talked about the similarity scores yet, so I'll leave that for now and we can discuss that a bit later. If you set it to cutoff equals 0, it will always find the best matches, regardless of whether those matches are any good or not. So you can use the cutoff value to filter out matches that are not that great. I'm also going to go ahead and convert this line of code on line 20 into a function that'll be a little bit easier to use. This function is called getBestMatches, and it's going to take the from vector and the to vector, and it'll return the best match for each observation in the from vector. Just as an example, I can use this function to find the best matches for each observation in the from vector to the to vector, and then I'm going to store the results in a variable called difflib matches. So if I look at the length of from vector, it's 95, and the length of the to vector is 94. So we want to actually find a best match for each of the 95 observations in the from vector. And if I run that function, we can see that the difflib matches object contains 95 observations. Okay, so now that we've got these matches, we should probably determine how good these matches are. In order to do that, we're going to use sequence matcher from the difflib Python package. So first I type sequence matcher, then a $, then I'm going to use new, open bracket, and then the arguments that it's going to take are the 2 strings that you'd like to find the similarity score between. For this example, we want to find the similarity between the first observation in our from vector and the match that was found for that observation, which is located in difflib matches, the first observation. And then to actually get the ratio, I need to enter another $, and then ratio with brackets. If I run that, I see that there's a similarity score of 0.857 and change between those 2 strings. Now the similarity score is going to range between 0 and 1, where higher values mean that the strings are more similar to one another. If the strings are perfectly identical, the similarity score would be exactly 1. So here, since we had a similarity score of 0.857, it tells us that the strings are fairly close to one another, but they do have some small differences. And intuitively, this makes sense. If we look at the 2 strings that we're comparing, they do look fairly similar. Really, the only difference is the comma and the 1 versus the dash and the word 1 being written out. Okay, I'm also going to turn this into a function so that it's a little bit easier for us to use. I've also gone ahead and vectorized this function so that we can pass it vectors rather than just single strings that we'd like to compare. So now if I want to get the similarity scores between my from vector and each of the best matches that we found, I can use the getScore function. And I'm going to assign the result to a variable called difflib scores. Difflib scores should have the same number of observations as both our from vec and our difflib matches, which we can see is true. It's 95. Now, if I look at the first few observations in my from vec, I can see the best matches for each of those. And now I can also see the similarity scores for each of those matches. We can see that some of these matches were a lot better than others. Remember, the higher the score, the more similar the two strings are. My apologies, I just realized I made another small mistake when I was speaking earlier. I said that the sequence matcher was from the difflib package, but in reality, the way that we're using it here is actually from the fuzzywuzzy R package. Ultimately, fuzzywuzzy R is calling sequence matcher from difflib, but in order for this getScore function to work, you will need to load the fuzzywuzzy R package. Okay, so earlier I mentioned that there are some issues with the fuzzywuzzy R package, and here is where that rant comes in quickly. At the time that I'm making this video, March 25th, 2022, this is a problem that I've been experiencing for months with this package. It is entirely possible, if you're watching this video down the road, that these problems have been fixed by the package author. But as of right now, there are some slight complaints that I have about using the fuzzywuzzy R package. My first complaint is that the fuzzywuzzy R package is doing the exact same thing that we just did, except not as well as we just did it. And when I say not as well, what I mean is we don't have as much freedom to control the parameters in the way that we just did when we did this more manually using difflib. So for example, from the fuzzywuzzy R package, there is a getCloseMatches function. It's going to do the exact same thing that the get_close_matches function from the difflib Python package does. And it's going to take the same syntax, except we have less freedom with it. For example, if I try to find the best match for the first observation in my from vector, and I want to set the cutoff to 0, it will not let me do that. It tells me that the cutoff parameter needs to be greater than 0 and less than or equal to 1. And personally, I don't like that. I want to be able to choose the best match regardless of what that score is, and then I can make a decision down the road about whether or not those matches look right based on the scores. The fuzzywuzzy R package is calling the difflib package here anyways, so for me personally, I prefer to just use difflib directly so that I have more control over how I'm using that package. The second piece of criticism that I have about the fuzzywuzzy R package is about the documentation. The documentation is a little bit misleading. For example, it sort of leads you to believe that you're always using the fuzzywuzzy Python package when you're using the fuzzywuzzy R package, but in reality, depending on how your system is set up, you're not necessarily using the fuzzywuzzy package. You might not even need to have the fuzzywuzzy Python package installed. And in the examples that we just used, even though we were calling fuzzywuzzy R, we were really only using difflib. Obviously, that's a matter of reading the documentation really carefully, but I would just caution you, since you might think that you're using one algorithm when in reality you're using a different one entirely. And my third criticism of the fuzzywuzzy R package is that there are a lot of errors that can occur. When you Google fuzzywuzzy R does not work, there are posts about how there's this attempt to apply non-function error for many of the functions in that package. Ultimately, if you know what you're doing, it's easy to work around this, but for newer R users, this can be a really frustrating experience. The fuzzywuzzy R package is great, but there are some things to be careful about. So if you're planning on using it, make sure you read the documentation extremely carefully. Thanks for listening to my side rant. Back to the topic of interest. Next, we're going to be looking at the polyfuzz package for fuzzy string matching. What I really like about polyfuzz is that it's actively being maintained and it has way more flexibility than difflib. Basically, you can create your own distance metrics and your own string matching algorithms. As the author of the package mentions, customization is a big part of polyfuzz. Speaking of which, the article that you're looking at right now is amazing. I highly recommend reading it if you're looking to use polyfuzz. It has some awesome examples of how to get started. It is focused on Python, but you can apply all of these same concepts in R, and I'll show you some examples that will help you do that. What you see here is sort of the basic example of how to use polyfuzz in Python. So here they're importing the polyfuzz package. They're specifying that they want to use the edit distance as their distance metric, and then they perform matches between a from vector and a to vector, just like we did before. Then you use a function called getMatches, and it outputs similar stuff to what we did using difflib, except it does it all for us. So before, when we had to make those two functions in order to get the matches and get the scores, polyfuzz does that for you, and it outputs it in a really nice, beautiful format for you to work with. So I'm going to follow this exact example, but I'm going to convert it into R code. So remember up here, I loaded the polyfuzz package and assigned it to an R object called polyfuzz in all caps. So here we can see we're going to use a polyfuzz function from the polyfuzz package. So here I'm using the polyfuzz function from the polyfuzz package in Python. And then I specify the string matching algorithm that I want to use. So here we're using edit distance. And in R, we do the exact same thing. We specify edit distance. Next, we're going to use a function called match on our from vector and our to vector. In R, I'm using the match function on my from vector and my to vector. And finally, to get the outputted results in that beautiful format that we saw, we need to use the getMatches function. So in R, I use $sign and then getMatches. That function is not going to take any arguments, so we can just leave the brackets empty. And voila, there we have it. If we look at the my model data frame, we have 95 observations. So for each observation in our from vec, we have found the best string match that's within the to vector, and we have the similarity score. As you can see, using the polyfuzz package is much easier than using difflib or than using fuzzywuzzy R. This was just using the edit distance, but there are a lot of different string matching algorithms that you can use from the polyfuzz package. I really encourage you to check out that blog post. I'll put the link in the description, as it has some great examples of how to use this package in really cool ways. The last algorithm that I want to show from the polyfuzz package is TF-IDF. Here we're going to be applying term frequency, inverse document frequency on character n-grams, and then use cosine similarity to determine how similar strings are to each other. This one is coming from polyfuzz.models. To access polyfuzz.models, we're going to use the polyfuzz object from earlier, then do $models. That should allow us to access the TF-IDF function from the polyfuzz.models. Then we can specify whatever options we want inside the TF-IDF function. I'm just going to use the default here just for the sake of creating the example. So we'll say n_gram_range is equal to, and since this is R and not Python, we're going to pass this as a vector. So I'm using the concatenate function to pass the options 3 and 3 for n-gram range. I'm going to assign this to an object. I'm going to call it my TF-IDF. And now if I apply the polyfuzz function on the my_TF-IDF object that we just created, we'll be able to use that model to get the matches. So we're using the polyfuzz function on the my_TF-IDF object that we just created. Then we need to use the match function on the from vec and the to vec. And our very last step, Just like with what we saw earlier, after we use the match function, we need to use the get_matches function. And I'm going to assign this to an object called TF-IDF results. I got an error because I accidentally forgot to put 2vec inside the match function. If I run that again, I still get an error, which is really strange. It turns out that to fix this error, if I comment out the my_TF-IDF line and I replace the my_TF-IDF with, in quotes, TF-IDF, I'm able to get some results outputted. Unfortunately, that means I'm not sure how to change the value of n_gram_range at the moment, but we are using the default value. So it should give the same results in theory if you were to do this in Python using n-gram range equals 3 to 3. If we take a peek at the TF-IDF results data frame, we get something with a very similar structure as what we had before. Again, we've got one observation per element in the from vector. We have the best match for each of those elements, and we have the similarity score. I just want to do a quick aside to mention that a good value for the similarity score is going to be completely different depending on the distance metric that you're using. It's sort of up to you as somebody analyzing the data to determine what is an appropriate similarity score for your purposes. For example, if we look at observation number 10, even though there's only a similarity score of 0.62, to my eyes, it looks like this match is correct. So it's sort of up to you to play around and explore the similarity scores and determine what cutoff value constitutes a correct match. If I look at the results that I got from when I used the edit distance from the first time that we used the polyfuzz package, and if we take a look at the same match on observation number 10, the same match was picked by both algorithms, but the similarity score is much different. So with TF-IDF, the score was 0.621, but with the edit distance, it was 0.872. So you're not always going to be using the same cutoff, and that's going to largely depend on what makes sense for your purposes. Thank you so much for watching this video. As always, I will post the code and the slides and any of the other resources that I've mentioned below in the description of the video and on my GitHub. If you liked this video, please subscribe to my channel so that I can continue to make content like this.